Hey, it's Cosmic Ray, the quantum mechanic. We're here to learn some chemistry. I developed a new kind of periodic table here to show electronegativity. See how big the circle is here, the empty one for fluorine? That means fluorine's going to take one electron, and then it'll be stable. Big circle, most electronegative element there is fluorine. You look next, you see the big circle for chlorine, the big circles for oxygen. Those are electronegative. So the most electronegative elements are on this side of the periodic table. Now when you look at this table design, it's neat because the bigger the circle, the more electronegative it is. Now when you look down on the other side here, behind me, where are we going there? Right. Cesium. Boy, this is confusing. Cesium. I thought I knew my periodic table backwards. I got it backwards. Right here, big asterisk, that valence electron is electropositive. This electron will be given up real easy. So cesium fluoride, this is the most electronegative compound that there is. Most electronegative element, electropositive. This is the most ionic compound that there is. Hey, it's Cosmic Ray, the quantum mechanic. I came up with a new periodic table design for you. This shows the ionic compounds. You see how fluorine's got the biggest empty circle here? That means it's the most electronegative. See, chlorine's got a big one. Oxygen has two big ones. They're electronegative. What that means is if you have an element like cesium that it will give up the electrons, cesium, most electropositive. So cesium fluoride, this is the most ionic compound that there is. Cesium fluoride. Cesium chloride, what ionic means is that it'll dissolve in water real easily. Cesium also, if you put it in water, like rubidium, potassium, or sodium, these things will give up an electron in a real exothermic reaction, meaning that this thing will spark around on the water. And if you can find solid lithium, pure lithium, be careful. Wear your goggles. Sodium, same way. The Grignard reaction that you'll hear about, when you throw these elements in water, any aqueous solution, they're going to react exothermically. Lots of energy is going to come out. So people think ionic bonds aren't as strong as the covalent bonds. Well, they are. Sodium chloride, there's a lot of energy in a salt thing. 800 degrees it would take to dissociate it, but you could put it in water and it does it by itself. So you got to know your chemistry here. Fluorine, most electronegative. Cesium, most electropositive. So this is your most ionic compound. You have electronegativity values. If fluorine gets a 4, cesium is considered a 1. So a difference of 3 is what is called a real ionic character. So cesium fluoride would dissolve in water. Cesium chloride would dissolve in water. Cesium oxide dissolve in water. When you compare the electronegativity values, anything above a 2.5 is going to be an ionic compound. Now hydrogen we list on both sides of the table of the elements here. Hydrogen has a 2.2, fluorine a 4. So this would form a covalent bond, hydrogen fluoride. This is a gas. Now what you find though is when you dissolve it in water, you will get hydrofluoric acid. And what makes it an acid in this case is that the proton, the hydrogen, is liberated in the water because the electron is going to stay with the fluorine. If it's electronegative, that means it's going to hold on to the electron. So fluorine, the most electronegative element that there is. Chlorine. What chlorine can do is it can form 1 bond or 3 bonds. Chlorine can also do what bromine is listed to do here, 5 bonds. Or, as it's listed down here, 7 bonds. This is where students get really confused. They're called oxyacids now. If you start bringing oxygens in, oxygens are always going to have 2 bonds on it. So a great way to do this is 2 for the oxygen coming in for 7. So you've got 2, 4, 6, and then a single bond. So 1 oxygen, 2 oxygens, 3 oxygens, a 4th oxygen is a single bond to it. If you get this down, this is the hardest Lewis structure that you'll ever have to draw. 7 bonds. We know now that electron pairs are how these elements bond. For each bond is 2 electrons. So 7 bonds, 14 electrons. But you can do it now, because if you go back and all the electron pairs from fluorine, there's 3 pairs, 2, 4, 6, and the single bond, that's the 7th bond. Fluorine doesn't do this because it's got a smaller so if you look over here, the size, look over here, the size of the asterisk is how easily they were given up. The more electropositive, the bigger the asterisk. So this is a pretty neat table of the elements to look at here. Calcium has 2, so what you learn is how these compounds form and what the ratios are. Electron pairs are how these do it. Nice table there, isn't it? Here's a table design I think is pretty neat. Here's a table that's pretty neat. To form proteins, there's 4 essential elements that are doing this here. You got a carbon, a nitrogen, an oxygen, and a little hydrogen. So if you ever played cards, diamonds, carbon bonds 4 bonds around it, so a diamond has 4 points. So always think carbon is what a diamond is, pure carbon. Tetrahedral they call it, tetra 4, there's 4 bonds on a carbon. Nitrogen has 3 bonds, so that could be the clubs. Clubs have 3 little things on it there. 3 bonds for the nitrogen is a club. Now the heart with 2 bonds for the oxygen bound to the carbon. Think of the 2 things on the heart, 2 little ovals before the point. So this is a double bond to the carbon, carbonyl they'll call it, and the little spades can be the hydrogen. So as you piece these together, this is the backbone for a protein. So these amino acids are hanging off, you'll see the R groups. But I think this is pretty neat, that just seeing how it repeats, because every set will be opposite. See where you got a heart here with the R group hanging down? Over here the heart's pointing up, which means it's reversed, so the R group on that side is down. So these rotate back and forth as they string along. Follow the hydrogens. The little spades, 2 are pointing up. Over here the 2 are pointing down. So the 4 main elements that make a protein backbone are the 4 suits of your cards. So if you like playing cards, you got hearts, which is a double bonded oxygen. You got the carbon for diamonds, that's the 4 bonds. The 1 for the spade is 1 hydrogen, so single bond there, and the 3 bonds for the nitrogen. So think of that. See how the clubs, hearts, diamonds, and spades. Now this is like the other table that we did, except all the circles are the same. So, well, they're a little bit bigger here. We darkened them in a little. So see how the fluorine. Fluorine's only going to take 1 electron, HF, CSF. That's the only bond fluorine is going to bond once. The octet is that predominant. But now you see the chlorine here,